going to be looking at polygenic inheritance. Now, in polygenic inheritance, this is actually looking at how features that show continuous variation are actually coded for. So with discrete variation, this is just distinct or discontinuous categories of phenotypes with just one gene involved. This is what we've really been looking at so far. Just one gene is involved with looking at, say, blood type or cystic fibrosis, or looking at the height of pea plants. They can either be dwarf or tall. Whereas continuous variation involves several genes that all code for the same characteristic. And because you can have these genes that are dominant or recessive for any of them, they actually show quite a range of different variation. So continuous variation is what we're going to be looking at with polygenic inheritance. Now, I've just put a few notes here. So polygenic inheritance, a single phenotype that's determined by more than one gene, and the phenotypes, the characteristics, exhibit continuous variation. And it's this cumulative effect of several genes that contributes towards the phenotype. And the key example that the syllabus wants you to know about is human height, but we're also going to look at a couple of others, and we're going to look at also skin colour as another example of continuous variation. So, what we're going to be doing is the following. First of all, we're going to look at just a normal dihybrid cross between two heterozygous parents. So this is something that you've done before. But this time in the grid, we're going to write the number of dominant alleles for each offspring, and then count the number of individuals who have either 0, 1, 2, 3 or 4 dominant alleles in their genotypes, and then plot this in a histogram. So this is easy, we've done this before. So if we've got two heterozygous parents, so if we're crossing AA, BB and BB, and we're crossing that with AA, BB, we're going to get these gametes being produced. And I'm not going to fill in the whole lot, but I'll show you, if we just fill in the top row, I'll show you what you need to do. And these notes are on OneNote for you to fill in already. Okay. And A, B, there. Okay, so now I won't do the whole lot, but we can actually count the number of dominant alleles. So this one here, 1, 2, 3, 4. This one has 3. This one also has 3, but this one only has 2. And if we go to right at the end of the Punnett square, looking at the cross between this one and this one, we can see that we actually have 0 dominant alleles in that individual. So with these two parents, who are both heterozygous, you can get a wide range of different phenotypes produced. And then what we can do, if I show you the filled in already, so I've done this one already, you can actually work out the frequency of each of this number of dominant alleles. So for 0, the frequency is only 1, whereas for 1 dominant allele, we've got 1, 2, 3, 4. So, and for 3 dominant alleles, sorry, 2 dominant alleles, we've got 1, 2, 3, 4, 5 and 6. And for 3 dominant alleles, it's 4, 1, 2, 3, 4. And for 1 dominant allele, it's 1. So what we can do here is now plot a little histogram to actually show the distribution of these different frequencies. So we'll just do our axes like this. On the x-axis, you put your number of dominant alleles. And here we put the frequency on the y-axis. So we've got 0, 1, 2, 3 and 4. And the frequency is 1, 2, 3, 4, 5, 6. Obviously, I'm just sketching this. It's much neater if you do it on graph paper, but it does nicely show how you get this variation in characteristics. So I'll just fill in my box. So then we've got 4 for the next one. Here we go. And we've got 6 for this one. And then 4 again. And then 1 again. Now, this is only looking at 2 genes. Many characteristics involve more. Height involves at least 3 or 4 different genes that we know of that contribute to cumulative to height. But what you're starting to see is the beginning of a normal distribution curve. And the next graph actually shows if we were to have 3 genes all contributing, say A, B and C, and we cross 2 heterozygous parents, you would actually end up with this normal distribution curve. And you can see that the more you add, the more it follows that particular pattern. And you always notice you get more individuals in the middle and far fewer at the extremes. So how does polygenic inheritance lead to continuous variation? How can we summarise this? So with phenotypes that exhibit continuous variation, several genes contribute to the same phenotype. And the number of dominant alleles inherited will contribute towards the phenotype in a cumulative way. And therefore, if 3 different genes are associated with one characteristic, a person can inherit between 0 and 6 dominant alleles. So this is 7 different phenotypes. And this creates intermediates between the extremes of the phenotype, which is continuous variation. But it's not just genetics that can contribute to continuous variation. We can also have environmental effects. So we've got these 3 particular phenotypes that show continuous variation. Height in humans, skin colour in humans, and coat colour in mice. I don't know if you remember that one. So what I want you to do is just have a think about how different environmental factors could affect these particular polygenic traits. And just before we finish, I wanted to show you this. This was in the news quite a few years ago about a couple, and they had 3 children, and through polygenic inheritance, they saw a wide variety of different phenotypes amongst their children in terms of skin colour. And this one particularly caught my eye, which was twin girls, but they are non-identical twin girls, so they will have just, the genes would have been inherited, just showing normal Mendelian rules of independent assortment, and you can see the variety that can be achieved here.